Hi everyone. Chapter 7 is a continuation of Chapter 6. In Chapter 6, we talked about the relationship between two quantitative variables. In Chapter 7, we'll find a model that represents that relationship. We'll interpret the model and we'll use the model. So I'm going to use the same example that I used at the end of the Chapter 6 video, where we had homes that were given in square feet in size and that had a selling price in thousands of dollars. So looking at this data value, a home that was 2,521 square feet had a selling price of $400,000. We looked at the scatter plot and we found the correlation coefficient, and we determined that this was a linear relationship that was positive and strong, and there were no outliers. So now that we have the relationship between these two variables with our actual data, we want to be able to use these data to predict the selling price of a house based on its size. And if we want to predict something, then we need a model. So since the form of our relationship is linear, it makes sense that our model is also going to be a line. Before, when we found the correlation coefficient, we said that it didn't matter which was our x variable and which was our y variable. But now that we're finding a model, it does matter. We want to make sure that the x is our explanatory variable and our y is the response variable. The response variable is the variable we're trying to predict, and the explanatory variable is the variable that we're given. So in this case, we would be given the size of the house, so that's our explanatory variable, and it's along the x-axis. And we're using that size to predict the selling price, which is on our y-axis. So to find this linear model, what they do, and of course we would use technology to do this, is they find the vertical distance between the line and the data point. They square this distance. They do that for all the points and add up all of those squareds. And whichever line has the smallest sum of all of those squared vertical distances is called the least squares regression line. It's also called the line of best fit, or I like to use the term linear regression model. So we're going to use our calculator to find the linear regression model. We've actually already done this because it's the exact same steps as finding the correlation coefficient. The linear regression model also has the same conditions. We want to make sure that the variables are quantitative. We want to make sure that the form is reasonably straight and that there are no outliers. So we're going to go to the exact same place. We've already turned on diagnostics, so this is done. We're going to enter the data into L1 and L2. It's really already done too, since we did that in Chapter 6. And then we're going to go to Stat, Calc, and Lin Reg. So exactly the same place, and let's do that here. So there's the data. Notice again that I have to be more careful here. I'm making sure that I'm putting the explanatory variable in L1 and the response variable in L2. Then go to Stat, Calc, and I always use number 4. Number 8's an option, but it's just more clicks away. I think number 4 is easier because it's quicker. So notice again, I need to make sure that the explanatory variable is the X list. So that's why I always make sure that the explanatory variable is in L1 and the response variable is in L2. Then this is already loaded for me and I don't have to change it. I can just go down to calculate. And we have this as our output. If I ask you for the linear regression line, don't write exactly what's on your calculator. Actually write the model. When we write the model, we use a hat over the y variable, so this hat. And what it does is it tells the reader that this is a model and that y hat represents a predicted value, not an observed value. And then since this is in the form of y equals ax plus b, and a is given as 0.0992 times x, plus the b, which is 160.2055. So I just rounded to 4 decimal places. You can round it 2, 3, it doesn't really matter. Some people, instead of using the x and y, they like to use the names of the variables, or maybe the first letter of the name of the variable. The first letter for both of these is S, so that wasn't really a good choice. But we could put the hat over the entire variable name, which is selling price, and then put size instead of X. This does make it a little bit easier to interpret your model when it comes to those questions. So looking a little bit more at the output, we want to get into where we can really interpret this. So it's important that we know all the aspects of the regression model. So size was the explanatory variable, so this was our x, and selling price is the response variable, so this is the y. The slope of this line is 0.0992. Remember in algebra, you didn't see it as y equals ax plus b, you saw y equals mx plus b, where m is the slope and b is the y-intercept. So we're using the same thing here. The number in front of the x is the slope and the constant's the y-intercept. So in this case, the slope is 0.0992 and the y-intercept is 160.2055. So interpreting the linear model. So y hat is used to estimate the average outcome for a given value of x. So let's say we have an example that says use the linear regression model to estimate the average price of all houses whose size is 3,000 square feet. So then what we would do is we are given the size as 3,000, so we're going to put that in for x. So we would have that y hat is 0.0992 times 3,000 plus the 160.2055. So you're really just putting 3,000 in for x and calculating y hat to get 457.8. Just remember that you should always think about this in terms of the context of the problem. So we would say that for 3,000 square foot homes, the average selling price is $457.8 thousand. Or you could write it like this. Just remember that the units in our table were in thousands of dollars. The y-intercept is the constant in the model, so in this case it's the 160.2055. And a lot of times we're asked to interpret the y-intercept. And we want to make sure that we're interpreting it in the context of the problem. So the y-intercept for a line means that when x equals 0, y equals that value. So in this case, if the size of the home is 0 square feet, the average selling price is approximately $160.2 thousand. So a lot of times the question is, does this make sense? So 2 points. First, of course, there's no such thing as a home with 0 square feet. But it could be that you could think about this as like a starting off point. However, when I look at this model, I see that my data started at about 2,400 with a selling price of $400,000. So 0 square feet is pretty far away from where my data started. And I'm bringing in kind of an extra little vocabulary word here. It says making predictions for values of the explanatory variable that are outside the range of the data is called extrapolation. We have to be very careful when we are trying to extrapolate something. And in a lot of cases with a regression line, you don't want to do it, especially if it's that far away. So even though we could say maybe this is just a starting off point, I would venture to say that this is not something I would look at any further because it's too far away from the rest of our data. A big thing that is really important is interpreting the slope. I have never been in or taught a statistics class where I did not have to interpret the slope all the time for a linear regression model. It didn't matter if I was in intro stats, advanced stats, a master's class in stats, it doesn't matter. We're always interpreting the slope. You will have to interpret the slope. So remember, I'm going to kind of make some notes up here. Remember the formula for slope from algebra is the difference in the y's over the difference in the x's. y2 minus y1 over x2 minus x1. We also called this the change in y over the change in x. For this particular problem, the slope is going to be the change in the selling price over the change in the size. And I can see that the slope is 0.0992, and I can always write this over 1. So we're going to create a sentence that describes this, and we're going to make sure that we're using the explanatory variable to describe the response variable. Also remember that the model is an average. So we start off by saying on average. Then we're going to start with the explanatory variable. For every 1 square foot increase in the size of the home, so I'm looking at the denominator. For every 1 square foot increase in the size of the home, the selling price increases by approximately $0.0992 thousand. Now, if you were to take 0.0992 and multiply it by 1,000, you would get this. So a 1 square foot increase in the size of the home will increase the selling price by $99.20. Now we can use this to answer some questions. Here's an example. Say we have 2 houses up for sale. One house is 1,900 square feet in size and the other one is 1,750 square feet. By how much should we predict that their prices will differ? So think about what the slope means. It means for every 1 square foot increase. So let's figure out what was the increase between 1,750 and 1,900. Well, if we subtract them, we know that it increased by 150 square feet. If we multiply that 150 times the slope, we will get the increase in the selling price. So I'm taking the slope here times the increase, and I'm getting a selling price of 14.9, again, remember the units, $1,000. If I actually write that in thousands of dollars, we'll get this. I don't mind whichever answer you want to write this in. That's why I'm writing it as both. You could either write $14.9 thousand or you could write $14,900. It's completely up to you. Residuals. We've actually kind of touched on residuals already because we use residuals when trying to find the linear regression model. The residual is the distance between the point and the line. So what we're actually finding is the distance between the observed value and the predicted value. And remember that the observed values came from the table, and the predicted values come from the line. So this is what gives us the predicted values. So if we want to find a residual, we're looking for the difference between these two things. So for example, say I want to find the residual for a home that is 2,555 square feet. Well, this is the size, so this is our x value here. And if I look at the x value for 255, I can see that the observed y value is 426. So looking at the table, I see that y equals 426. Then I need to use the linear regression model to find the predicted value. So I'll plug in the x into the model, and we'll get a predicted value of 413.6. The residual is the difference between these, and we always take the observed minus the predicted. So I take the observed minus the predicted to get a residual of 12.4. So we would then say for a house of size 2,555 square feet, the model underestimated the selling price by $12.4 thousand or $12,400. So notice that the model is underneath the point, right? The point is higher than the model. Therefore, the selling price, the actual selling price, is above the predicted selling price, and therefore our model underestimated what we actually saw. And in this case, it specifically underestimated the selling price by $12,400. All right, so I'm going to do this example in the next video.